Hello everyone, welcome to our presentations. Our group research topic is homomorphic encryption's principle and related applications. Nowadays, the most common cryptography is defined as two different mechanisms, symmetric and asymmetric key cryptography. And both of these mechanisms are mainly focused on how to ensure data security, to avoid disclosure of information. And those are some problems that we need to consider, as the creator cannot make any modification to the ciphertext after it has been created, and any modification to the ciphertext will cause errors in the final decryption process. Therefore, either the creator or receivers can only to store or transmit it. So, is there a situations the creators of the ciphertext want to make change to the original content after encryptions or after the ciphertext is sent? And the encryption and decryption process is overly complex and time-consuming. So what kind of solutions can help to solve these issues? Maybe homomorphic encryptions would be a solution. Homomorphic encryptions focus on the security of data processing instead of the security of data storage. It provides a function that no need to decrypt ciphertext but still can change the content of it. For example, we need a staff member to process a gold and get a piece of art, but we don't want the staff to store up gold in the process of working. Then use a scheme of the homomorphic encryptions can be a way to solve these problems. We put a gold in the locked box. The worker doesn't need to touch the gold, but can still work on it get some way. After processing, we only need to open the box with our own keys to get a gold artwork. We regard such a box as a cipher cryptographic algorithm, the lock of the box as a private key. Since homomorphic encryptions were defined in 1978 until now, it has been defined as a three-part, partially, somewhat, and fully. Partially homomorphic encryptions algorithms allow a certain operations to be performed as infinite number of times. For example, a particular algorithm may be additively homomorphic, means that add two ciphertexts together produce a same result as encrypting the sum of the two plain text. Somewhat homomorphic encryptions is a step up from partially. A somewhat homomorphic encryptions algorithm allow a finite number of any operations. For example, a somewhat algorithms may be able to support any combination of up to 5 additions or multiplications. However, a sixth operation of either type would cause an invalid result. The first fully homomorphic encryptions algorithm was invented in 2009 by Craig Ginto. A fully homomorphic encryptions algorithm allows an infinity number of additions or multiplications of ciphertexts while still producing a valid result. And this is a basic definition of the different scheme of homomorphic encryptions. My teammates will introduce more details of it.
Before we introduce the application of homomorphic encryption, let's first look at three types of methods with some examples, and then you will better understand why it is powerful and why it has not been fully used in practice. So as you can see from the definition of partially homomorphic encryption, it is relatively easy to design. If you imagine if you want to perform an infinite number of one operation on the ciphertext without changing its relationship between, with the plaintext, you need the algorithm to have some special properties in mathematics. So one example we could give is the RSA algorithm we learned in class. If you do the computation of RSA algorithm, you will find that it is multiplicatively homomorphic. So the multiplication you performed on the ciphertext will have the same effect on the plaintext. So once you understand the idea of partially homomorphic encryption, you will find many algorithms that support it, just like we did here. But you will realize that this approach is not secure, and it is meaningless if you are only allowed to perform one particular operation. So you can see from the timestamp that all discoveries of homomorphic encryption in 20th centuries are partially. But in the 21st century, the scientists found a new method called somewhat homomorphic encryption, which allows us to perform a limited number of additions and multiplications. So you may wonder why it is limited. We don't show the whole mathematics of why it is limited here, but just to give you guys an intuition. If you build if we build our encryption schema like this, it would be supportive of both multiplication and addition. So this is the setup of our schema, and this is how we encrypt our message. So you may notice that as we perform more and more operations, the value of the noise here and here will propagate and end up with a very large value. This large noise will ultimately affect the correct conversion between the plaintext and the ciphertext. So if we want our output to be correct, we need to restrict the number of operations when we encrypt the message. So the main idea is that we need to control the value of the noise. So somewhat homomorphic encryption looks cheap and complicated, and we can see the applications in some places later. But here, we should know that this limited type is not the end of the homomorphic encryption. It's just a stepping stone to the fully homomorphic encryption. So what is fully homomorphic encryption? It is the ultimate version of this technique that allows us to perform an infinite number of arbitrary operations. So looking at the end of the time step, we notice that a computer scientist called Craig Gentry has found a method to accomplish FHE. So again, we don't expand the math here, but we can use the previous example from somewhat homomorphic encryption to explain his work. So the basic idea is to periodically update the ciphertext here and here, so that we can refresh the noise value to 0 when it tends to be out of control. By doing this, we can perform an infinite number of operations while generating the correct match. Gentry's idea seems to be the most secure way to associate with third-party cloud platform. But since it requires the computer to perform an incredible number of computations and store a massive amount of data, its viability is worse than somewhat encryption. So now we know that efficiency is the problem with homomorphic encryption. Looking at the efficiency in the figures, we see that the keygen function takes more than 2 hours to compute, and the public key size is very large. It's more than 2.3 gigabytes. So with such efficiency, the fully homomorphic encryption is not destined to be used immediately. So, but as we said before, somewhat homomorphic encryption has already provided us a cheaper and relatively secure way to process our data in some areas. So next, we will introduce how homomorphic encryption works with cloud computing and how it provides security to users today.
According to the process diagram on the right side, Alice would like to process the data by function f. However, due to the local machine limit, she requires extra resources to run function f on the data. Therefore, she sends the encrypted data by homomorphic encryption and the function f to the cloud. The cloud then evaluates the data under the function f and sends the output to Alice, which is also encrypted. Then Alice can simply get the desired output by the function f on the data without cloud knowing the data itself, as the data has been encrypted by the key of Alice all the time during the process, hence protecting the security of the user data. So before the technology of homomorphic encryption is introduced in cloud computing, the cloud needs to decrypt, join, compute, and encrypt again on the output, then save to the cloud or send it back to the user. However, homomorphic encryption helps the cloud become more efficient by cutting the join and encrypt time, as the data is encrypted by all the way during the homomorphic encryption process. However, there are some challenges that need to be considered during homomorphic encryption implementation. One is the restriction by functionality. The homomorphic encryption only supports one type of operation. So if an application requires multiple operations, the homomorphic encryption will be restricted. Additionally, using homomorphic encryption in the cloud computing, the delay of the processing time on the cloud will be heavily dependent on the size of the encrypted message. And lastly, the fully homomorphic encryption scheme, which is mentioned at the beginning of the presentation, is extremely slow and requires large memory spaces. And this is the end of our presentation. Thank you for listening.